In the next slide, we consider selection criteria for optical thin film and materials. What are ideal thin film properties? Ideally, an optical material with surface properties or chemistry that's inert to chemical reaction with rubidium, but also limits or block rubidium diffusion. So this particular material will likely be close to 100% optical transmission uh, or absorption, much less than 10 to the 3 per centimeter uh, from Polker, 1979. Refractive index close to that of DePaul gain medium, which is approximately unity or 1, very close. The highest optical transmission between 760 nanometer to 900 nanometer, even though we're more interested in 780 to 795 nanometer and the midband of that. The optical material should be ideally hydrophobic and resistant to humidity, so very resistant to water vapor. Good refractory properties, which means high melting point above 200 degrees Celsius, low coefficient of thermal expansion. In other words, the material shouldn't expand quickly when heated. This is to avoid cracking in both the expansion mode, the higher temperature mode, as well as in the cooling mode. The high enthalpy of formation, strong chemical bonding. In other words, the material should have high bond dissociation energy, high ionization energy, high lattice energy, and high electronegativity. Match lattice constant to the substrate would be preferred. Fused silica or other substrate, the lattice constants matching would be excellent to uh, make sure that the wavelength of light will pass much more easily. Resistant to chemical etching, and in the case of matched lattice content, the bonding also would be much better in that case. Resistant to chemical etching, laser damage, mechanical and thermal shock, high surface accuracy, wavelength resolution, and surface quality, or scratch and dig. Minimum birefringence, in other words, the material should not have more than one index of refraction to the extent as possible. It should have very low dispersion and low inclusion or bubbles. So in the next slide, we're ranking the thin films of optical material for DePaul optical windows in terms of their properties. So these optical materials could be magnesium fluoride, calcium fluoride, silicon dioxide, aluminum oxide, magnesium oxide, zirconium dioxide, tantalum pentoxide, and titanium dioxide. Refractive index is as close to 1.4 as possible, which magnesium fluoride would seem to be number one there as far as a match. Um, Calcium fluoride would be next, followed by silicon dioxide, and then magnesium oxide, and so forth. So, zirconium dioxide would be the least in terms of refractive indexes. So the closer the refractive index, the easier the transmission of power, and the less things you have to do to make the light behave itself going through for 100% transmission. So even though zirconium dioxide would be the least of these in terms of when I say least, really the highest refractive indexes. So it will bend the light more, could lead to more losses. It can actually be manipulated to by the use of combination of dielectric stack, as we will see later on, to provide close to 100% transmission. The optical transmission range, most of these cover the 780 to 900 nanometer required for DPAL. They're mostly broadband, so you're looking at anything from as low as I guess here 120 nanometer all the way up to 10 microns. So with in most cases greater than 85% transmission. So in case magnesium oxide, that's actually quite low, but If the other parameters are okay, that could still potentially be used. But so anyway, this optical transmission range just really tells us is it within the range of what we're looking for as far as broadband optical transmission for a DPAL. Standard enthalpy of formation. The tantalum pentoxide actually has the highest, and from theory, this is indicative of very strong bonding, and so you end up with tantalum pentoxide as being a number one candidate in that category. Aluminum oxide would be number two, titanium dioxide would be number three, and so on and so forth. So anyway, the indication for one category doesn't mean it's going to be good for everything. So all of these parameters, melting point, that's 2852 for magnesium oxide, very, very good. Zirconium dioxide just behind that with 2715 degrees Celsius, and so on and so forth. So, all of those are within acceptable melting point ranges for DPALs. Um, the resistance to humidity, most of them are, and we found that calcium fluoride is not, magnesium oxide is not, and this is just based on the literature and further testing. In the case of calcium fluoride, the coefficient of thermal expansion, the number one in this category is silicon dioxide, fused silica, and so that will expand the least relative to the others. Tantalum peroxide, would be second in that category. So, and so on and so forth. So anyway, none of these by themselves make these properties make any particular optical material from this list the ideal candidate, but this is a starting point to selection of the thin film for the DPAL optical window. So in the next slide, we dig a little bit deeper, and we find lattice constants, lattice energy, bond dissociation energy, density, and topological surface area. So our list become a little bit narrower, and so the thin film materials are now on the list are silicon dioxide, aluminum dioxide, uh, or aluminum trioxide, really. Um, so in the next slide, we dig a little bit deeper, and we now look at lattice constant, lattice energy, bond dissociation energy, density, and topological surface area. And we find that the list now narrows to silicon dioxide, aluminum oxide, zirconium dioxide, tantalum pentoxide, and titanium dioxide. And those have in the category of lattice constant pretty much they're mostly of the same order except for titanium dioxide, which is much lower. So in the next slide, we dig a little bit deeper to determine other parameters which might be used to down select or particular material for damage resistant optical coatings. We consider lattice constant, lattice energy, bond dissociation energy, density, and topological surface area. The thin film materials now being looked at this point would now be silicon dioxide, aluminum oxide, zirconium dioxide, tantalum pentoxide, and titanium dioxide. So we start with the average lattice constant. Typically, films of different materials grown on the previous film or substrate are chosen to match the lattice constants of the prior layer to minimize film stress or cracking. So the average lattice constant can vary quite a bit depending on the purity of the thin film. So in particular, silicon dioxide pairs very well with tantalum pentoxide, and aluminum oxide pairs very well with zirconium dioxide within the context of closest matching lattice constants. So we have titanium dioxide being extremely low as far as the lattice constant, and so not as perfectly matched. Next, we move on to average lattice energy, and the lattice energy of an ionic solid really is a measure of the strength of the bonds in that ionic compound. And in the case of the uh, aluminum oxide, has the highest average lattice energy, followed by silicon dioxide, followed by uh, you know titanium dioxide, and zirconium dioxide, then by tantalum pentoxide, which actually seems to have um, an order of magnitude lower average lattice energy. Average bond association energy uh, uh, pretty much determines the energy required to dissociate the bonds. And so within the thin film, so that translates to silicon dioxide being about 799.6 kilojoules. Uh, Tantalum pentoxide is of the same order, magnitude 799.1, followed by zirconium dioxide, titanium dioxide, then aluminum dioxide is actually much lower than any of those. The average density is another parameter which basically, the denser the material, the more tightly packed the material is, and so what you have is zirconium dioxide being the second highest density. Tantalum uh, pentoxide is extremely highly packed, almost twice any of the other ones. Thin film, 8.2 gram per centimeters cubed. Then you have now silicon dioxide being of pretty much similar order to aluminum oxide, somewhere for around 4 as well that of titanium dioxide. So another parameter is the topological surface area of a molecule, usually used in medicinal chemistry as a metric for optimization of a drug's ability to permeate cells. In our case, the assumption is that the lower the topological polar surface area, the less the rubidium is able to penetrate or diffuse into the thin film. However, tantalum pentoxide shows the smallest topological surface area by an order of magnitude, uh, but no firm conclusion can be drawn on its relationship to rubidium vapor resistance and penetration. So just to review a few of these materials, tantalum pentoxide is a high refractive index material. It forms durable, hard, scratch-resistant coatings, which in addition have high threshold resistance to laser radiation damage. Um, they're usually mostly paired with low index materials such as silicon dioxide uh, to create low stress multi-stack coatings. Tantalum oxide is well known for its applications in the telecommunication industry. They're well suited to operate with neodymium YAG lasers, has low absorption in the IR region, and so it also has the highest density. So it definitely has a high potential to be considered for resistance to atomic rubidium as a thin film.